All right, in this video I'm going to show you the method of Frobenius, and I'm only going to include the case where we get two different linearly independent solutions from this method. I'll include the other ones in later videos. Okay, so we're going to consider a of x, y double prime, plus b of x, y prime, plus c of x times y is equal to 0, where we're going to restrict to the case where x equals 0 is a regular singular point. Okay, so if some other number is a regular singular point. Okay, so this method is for regular singular points. If some other number is a regular singular point, such as 2, we'll simply make the substitution t equals x minus 2 to reduce it to the case where 0 is our regular singular point. All right, so let me explain ahead of time what it is we're looking for. Okay, so we're looking for some number r, which is not necessarily an integer. The method of Frobenius seeks a solution of the form y equals x to the r times the sum from 0 to infinity of c sub n x to the n. Or we can just bring that r, x to the r inside and write that as x to the r plus 1. Sorry, x to the r plus n. Okay, so that's called a generalized power series. All right, so let me illustrate the method through an example. I'm not going to go through the derivation of it because it'll make it a really long video. So for our first example, find the Frobenius series solution, so it means find the generalized power series solution of 4x y double prime plus 2y prime plus y is equal to 0 for x is bigger than 0. So for example, then we don't have to worry about taking the square root of x and needing to put absolute values in. Okay, so just the simplest case. So the first step that we're going to do is we're going to take our differential equation, again, having checked that x equals 0 is a singular point, in which case the regular series method won't work. So if x equals 0 is a regular singular point, then we'll write it in the form x squared y double prime plus x p of x y prime plus q of x y equals 0. So let's go ahead and write this one in that form right there. All right, because of this 4 here, we want to first divide by 4. And that's only x to the power of 1. We want x to the power of 2. So basically we're going to multiply this by x over 4 to get it as just 1 times x squared. Okay, so again, we want to write it as x times p of x. So now here is our x, and our p of x is a half. Our q of x times y, so q of x is x over 4. Okay, next we'll form the equation to allow us to find out the values of r that will help us in this scenario. All right, so that equation is called the indicial equation. And that is r times r minus 1 plus p sub 0 r plus q sub 0 equals 0, where p0 is the limit as x goes to 0 of p of x, so what's being multiplied by the x, and q0 is the limit as x goes to 0 of q of x, so the whole thing that's being multiplied by y. Okay, so you see here, it's really helpful if we get it in a particular form and then define the indicial equation based on that form, so we don't have to derive it every single time. All right, why don't you press pause and go ahead and find p sub 0 and q sub 0 for this particular case. Okay, you should have found that p sub 0 is the limit as x goes to 0 of a half, which is a half, and q sub 0 is the limit as x goes to 0 of x over 4, which is just 0. Okay, so p sub 0 is a half, q sub 0 is 0. So let's go ahead and put those into the indicial equation and then find the values of r. Okay, so the equation we need to solve to find r, which you'll remember, are the powers of x in our generalized solution, our generalized series solution, and therefore are called exponents. So the values of r are called exponents. So go ahead and press pause and solve this equation for r to find those exponents. All right, so you should have found that r is equal to 0 or 1/2. All right, so each of these, we'll apply them one at a time, and each of these is going to give us our two linearly independent solutions to our differential equation, and therefore we'll get the general solution from that. So let's start by using the value of r equals 0. So then our power series, you'll remember, our generalized power series took this form, the sum from 0 to infinity c sub n x to the r plus n. So if r is equal to 0, this simply becomes 0. And it's actually just a regular old power series. So we have the sum. So then y will take the sum as n goes from 0 to infinity of c sub n x to the power of n. All right, and so the process is pretty much the same as for power series from here on out. All right, so we need to take this and plug it into our differential equation here to see what our coefficient should be. Okay, so we need our derivatives. So this is, I'm going to just quickly go over this one because it's the same as for the regular power series. So we'll get y prime is equal to the sum as n goes from 1 to infinity of n c sub n x to the power of n minus 1, and y double prime will equal the sum as n goes from 2 to infinity of n times n minus 1 c sub n x to the n minus 2. Okay, so we take each of those and plug them into the differential equation. So we get 4x y double prime plus 2y prime plus y is what we're looking for. So we'll get 4 times x times this guy here. I'll go ahead and do it out the long way. Then plus 2 times our derivative. Then plus just our original. All right, so we want to rewrite this so that we have, I'll go ahead and choose that each one of these will have x to the power of n. So I'm going to go ahead and get rid of this x out front and replace that with an n minus 1. Okay, so I need to add 1 to this, so I'll subtract 1 from this. I also need to add 1 to this, so I'll subtract 1 from this. Okay, so we're going to rewrite both of these series so that they have an x to the power of n in them. All right, so for this one here, again, we're shifting n up by 1 here so that we are, or in other words, we're adding 1 to n here to get that to the power of n. So we have to add 1 to each of these n's, and then we have to lower this guy by 1. Here we're adding 1 again, so I add 1 to the n, so it gives us n plus 1, add 1 to that n plus 1, and then we have to reduce that by 1. Okay, so let me go ahead and combine this into 1. All right, finally, in order to combine these three series as one, just one term, we will have to extract the 0th term from these two so that each series starts at the same spot. Okay, so we'll extract the 0th term from here and the 0th term from here. Okay, so the 0th term of this first one, we have 2, and then 0 plus 1 is 1, and then c sub 0 plus 1, x to the power of 0. And then here, when n is 0, we get simply just c sub 0. And then we can bring all these three together now, starting at n equals 1. Okay, all right, so now that will equal 0 because the left-hand side of the equation is set equal to 0 on the right-hand side. All right, so from this we know that 2c1 plus c0 should be 0, and then all of these guys should be equal to 0. Okay, so we get c1 is equal to negative 1/2 c0, and then this right here is going to give us the recurrence relation. So why don't you press pause and clean this up a little bit to find the recurrence relation. All right, so we can factor out the n plus 1 times c sub n plus 1 from these first two. So then we're left with a 4n and a 2 there. And then we can factor out a 2 here. So we get 2 times n plus 1 times 2n plus 1 plus c sub n should be 0. So if we solve that for c sub n plus 1, we get negative c sub n, and we can put that 2 inside, so it's a nice little pattern, 2n plus 2 times 2n plus 1. Okay, and so this is going to be true for n greater than or equal to 1, because that is what the powers here start at. All right, so we simply now need to find the pattern. Go ahead and press pause and start to look for that pattern by plugging in values of n starting at 1. All right, so when n is 1, we're going to find that c sub 2 is c0 over 4 times 3 times 2. When n is 2, we get negative c2 over 6 times 5, so negative c0 over 6 factorial. c4, we get c0 over 8 factorial, so here you can see what the pattern is. The factorial, so we have a c0 on the top. It's going to alternate between plus, minus. And what's being the amount of factorial is double the subscript here. So we get c sub n is negative 1 to the power of n, c sub 0 over 2n factorial. So let's take a quick glance up to see what that was supposed to go to. So those were the coefficients in this right here. So we're going to find that y is equal to c0 times the sum as n goes from 0 to infinity, negative 1 to the power of n. Okay, c sub n is the coefficient of x to the n, so x to the n over 2n factorial. And notice that the coefficient of c0 is supposed to be 1, and it does follow that pattern. If n is 0, this is 1. This is 0 factorial, which is 1. And x to the 0 is, even though 0 to 0 doesn't work, that's kind of our shorthand for 1 as well. Okay, so that's our solution coming from r is equal to 0. Now we have to go through the exact same process and find the solution that goes with r equals a half. All right, so we seek a solution now of this form right here, c sub n, sum from 0 to infinity, c sub n, x to the power of n plus a half. So as in the case above, we find the derivatives of this and plug it into the differential equation here. 4xy double prime plus 2y prime plus y. So I'm going to give you the formula for the derivatives here. So if we have y equals the sum from 0 to infinity of c sub n x to the n, or n plus r in general, so make that an n. So I'll give you the formula for the derivatives right here. And I'll leave it for you to check by actually doing it out term by term that this really is the case. Okay, so in particular, you'll see that these in general start at the derivatives in general will start at 0, because unlike the regular power series case, our exponents here might not be positive integers. Okay, so we might not get terms canceling out by differentiating, like c1x. If we differentiate it, we just get c1. Okay, so x's go away in those cases. Okay, so again, if you don't believe me, you can write this out term by term and differentiate it and see what you get. Okay, so in particular, for this case, our r value is a half. So these are our derivatives with r equal to 1/2. Okay, so plugging in the value of r that we have, which is a half, we find that this is our generalized series that we're looking for. Here's the derivative, and here's the second derivative. Okay, so go ahead and plug these into the differential equation. Okay, so we plug them into the differential equation. 4xy double prime plus 2y prime plus y equals 0, but just work on the left-hand side so far. So we have 4x times y double prime. So we have a 4 here. These are the coefficients of x, and then we have to multiply this by x, so that's going to increase the power by 1. Okay, so our power is going to be n minus a half. Then we need 2y prime, which here in the process of finding that, I realized I had put n plus r minus a half. It's really just it becomes really just n minus a half. Okay, so I fixed that mistake. So 2n plus a half c sub n x to the n minus a half, and then times just our y. Okay, so here we can now set that equal to 0. So we should get these powers of n all to be the same. Okay, so let's maybe just, it'll be a little bit easier if we just take this one and make it b to the power of n minus a half to match these two. So we'll decrease the value of n by 1 in each of these, and then we have to increase it by 1 in the starting point here. So now we see that this starts at 1, so now we have the same power of x in all of them, but this starts at 1, so in order to combine all the summations, we need to extract the 0th term from each of these. Okay, so why don't you go ahead and do that, and then combine all the sums. Press pause while you do that. Okay, so when n is 0, we get 4 times a half times negative a half, c0 x to the negative a half, and then plus when n is 0 here, we get 2 times 0 plus a half, so it's 2 times a half times c0 x to the power of n minus 2. Okay, so you can see here that this coefficient is equal to 1, and this coefficient here is equal to negative 1. So in fact, these first two terms totally cancel one another out. And then I have the sum from 1 to infinity of all of these summons. So I went ahead and took this 4, split it up into 2 times 2. So I put 1, 2 into the first, so 2n plus 1. And I put the other 2 into the second, 2n minus 1, c sub n. Then here I took the 2 and distributed it, 2n plus 1, c sub n. And then here we've got our c sub n minus 1, and all of those times x to the power of n minus 1 half. Okay, and that equals 0. All right, so why don't you press pause and work on finding the recurrence relation. All right, so you should get, if you factor out a 2n plus 1 and a cn from these first two terms, then we have 2n minus 1 plus 1 left, so 2n left there, and then plus this c sub n minus 1. Then solve for c sub n, we get negative c sub n minus 1 over 2n times 2n plus 1. Okay, and so that's for n from 1 to infinity. So go ahead and look for your pattern here. Okay, starting with c1, so that's going to be negative c0 over 2 times 3, which is, I sort of kind of saw I might be getting factorials in this, so I went ahead and wrote that as 3 factorial. And then c2, so negative c1, so negative this over 4 times 5 simply becomes c0 over 5 factorial. If we, check one more term to make sure, we're going to get that it's negative c0 over 7 factorial. So in general, we have c sub n is equal to negative 1 to the power of n. Okay, so when it was 3, it was negative. When it was 2, it was positive. When it was 1, it was negative. So negative 1 to the power of n, c0. And then the relationship between the subscript and the number in the factorial. So here, when it was 3, it was 7. When it was 2, it was 5. Okay, so we could see that 2 times n plus 1 factorial is what our denominators will be. All right, so these guys were the coefficients of our series right here. So I'll go ahead and plug those in. Okay, so once again, we can check that we can, even though these were for n greater than or equal to 1, we can include n equals 0 here, because when n equals 0, we get c0 on the outside times negative 1 to the 0, x to the 1 half over 0 plus 1 factorial, so over 1. And that is indeed what the first coefficient of our series should be. All right, so our two linearly independent solutions are this one here in purple and this other one here in purple. Okay, so those are our two linearly independent solutions. We multiply both of them by an arbitrary constant and we get our general solution. So here's our general solution, and I'm going to show you that these are actually power series for two functions that we can write in terms of elementary functions. Okay, so because of this 2n factorial, the negative 1 to the n, I'm thinking cosine, and this 2n plus 1 factorial, negative 1 to the n, I'm thinking sine. But remember that the exponent has to match the number in the factorial. So we can do a slight little modification here. So if we replace each x with the square root of x, then because of properties of exponents, we get these two quantities here. So root x, we could first square it so it becomes x, then to the power of n. here we can take this 2n plus 1 times the power of 1/2. So 2n plus 1 times 1/2, which becomes our n plus 1/2. So in fact, our solution can be written simply as y equals a1 times the cosine of the square root of x plus a2 times the sine of the square root of x. Okay. In general, you're not going to be able to find a nice closed form for your series solutions. All right, so that illustrates the method of Frobenius. Okay, so again, to recap, I'm not going to do another example here because the hard part really is once you have the first two steps down is the hard part is 1, not making careless mistakes. Okay, and 2, just writing out your terms to find your pattern. And again, those are simply just the same ideas as in the other series solutions video. Okay, so what we do is we first write our equation in the form of x squared y double prime plus xp of x y prime plus q of x y equals 0, where we confirm that x equals 0 is indeed a regular singular point. Okay, and again, if it's not, then as I mentioned here, make the substitution and that will turn it into a differential equation where t equals 0 is a regular singular point. Okay, so then you simply will, so like I said, write it into this form here, and then you form your indicial equation right here, where, so p0, we take the limit as x goes to 0 of this multiplied by the x. For q0, we take the limit as x goes to 0 of the coefficient of y. Okay, those give us the powers of r, and then we just kind of plug them in and find them individually. And where is the other one? So yeah, okay, so here r is 1/2. I multiplied my old series solution by x to the power of 1/2 and then proceed as you